You're the first recipients of the logo. We just cleared it, we got it done. Yeah, the logo's done, so this is the first use of our logo. We finally, after a bunch of conniptions and minor tweaking, I think we're done with it. All of the font may change, but that's okay. Okay, this will be the science of climate change. There'll be 2 lectures. This is part A. Okay, and this is taken from UC Irvine at around 7 in the morning. One morning, it's sort of an ominous color background, early red clouds from under sunset. And so it shows that you can actually see the mountains and you can see the snow in the mountains. So it's not bad. All right, so, oops, I work this a little faster than I thought. Okay, so remember, this is our series of lectures coming up, so it's 1 a week. I'm doing Climate Change 1, which is sort of the science of it. Climate Change 2 will be impacts and adaptation on people. We'll go over. And then we have Diane Pataki doing biodiversity and ecology and so on. Don Dapta may swap because he may have a conflict there, but there may be shift. But for those of you who are here, it doesn't matter anyhow. But those who are planning, if somebody wants to see one lecture that you know, make sure that they look it up because some of these may shift, but otherwise we're open to that. So, as I said, I've shown you the 2 booklets that go with it, okay? These are the founding documents that have driven climate change research in the last 2 decades. They did not drive climate change research for the previous 100 years. That was driven by more scientific curiosity and some issues about CO2 that have been known for maybe 30 years, 40 years. But the Framework Convention really started driving climate change by having governments demanding to know what's happening, okay? And so we have the Framework Convention, and then we have the Kyoto Protocol. Conventions are feel-good documents. They generally have very few restrictions, okay? They are meant to do, they have principles behind them and goals. They do not have detailed agendas. They do not have penalties. Kyoto Protocol has penalties. It has exact requirements for reductions. The Kyoto Protocol exists under the Framework Convention. Next week, we'll look at some of the document details about why protocols, the Framework Convention is set up to have protocols put underneath it. So everyone signed, basically every government, as of 2003, I didn't look up, maybe more than that because of some countries splitting up, the numbers are only 190, have ratified the Framework Convention. Okay, I think the only governments that haven't are things like Iraq, Brunei or something, there's some very obscure places, Somalia, some dysfunctional places. Kyoto Protocol basically was ratified in 2005, went into force in 2004, went into force in 2005. Everybody now, even Australia signed on, everybody with the US has basically signed on. Once again, but the Kyoto Protocol we look at is really a document with fixed commitments, and the US is not going to sign on to it. And everybody's now looking at what's the next step after Kyoto. We'll do that later. The key driving force is Article 2 of the Framework Convention. The Framework Convention is fairly long, several pages. Article 2 is only this paragraph. Probably as much time went into Article 2 big paragraph as went into the rest of it. It's very carefully crafted, it's very carefully worded, probably a lot of negotiations, compromise and everything. The key issue is in blue. The convention's objective is to stabilize greenhouse gases at a level that prevents, quote, dangerous anthropogenic interference with the climate system. It doesn't define what dangerous anthropogenic interference is, but it leaves it somewhat open. Okay, that's, yeah.
So what is anthropogenic?
Anthropogenic is us, so that for some reason, anthropogenic has become a word it's been adopted for the last 25 years, and it probably isn't in the old dictionaries, but we knew that that is human caused, of human origin. Okay, and so there's even getting silly, like the current epic is the Anthropocene, because we have changed the climate and the globe so much due to land use and climate and many other things and ozone issues that we now are at a different geological epoch, people have argued. So anyhow, that's a catchy issue. So dangerous, anthropogenic, meaning human-caused climate change. All right. So what is the IPCC? Okay, now we're getting down to the science issue. This is sort of a mix of IPCC people. It's a bunch of assessments, a bunch of people. They won the Nobel Prize. Got very lucky in 2007, okay, along with Al Gore. And who was they? It's a whole bunch of people. There are very few permanent people with the IPCC. It gets reformed every few years. The governments create it, have it do assessments and keep going. So there's a chair long-term, but basically people keep rotating. It's the science behind the Framework Convention. Okay? The IPCC is mandated to deliver assessments and scientific numbers and values that then the Framework Convention feeds into its negotiations and uses. And so the purpose is that there will be a single international assessment of climate, that the governments accept the assessment, which they do. Okay? The governments do not argue. I mean, you find arguments about IPCC climate change science. You don't find the governments arguing because they've agreed to accept it. Okay? That means you ask all the governments. It's only outside there you get all the squabbles about, well, is it right or wrong, whatever issues. No, most of it has been accepted by all the governments, so that when they negotiate, they will argue over, well, if this is the last assessment, and this is what we said, what does that mean? You should give up, and we should give up in terms of climate mitigation, and who's responsible for what. So this is not usually fought over. Why? Because you'll see the government, plenty of the government actually go through and rewrite, work over, check it out. This is a sequence of assessments. They're out of order, 1990, 1995, 2001, and 2007. Those are the 4 major assessment reports. It's said to be at 5-year intervals, but fortunately it's been spacing out longer. It went 1990, 95, then it went 95, 2001, then 2001, 2006, and then 2006, 7 goes to 2013. So they've been stretching them out to 6 or 7 years, thank God, because otherwise they're an awful lot of work on the community. They take an immense amount of effort, as you can sort of look at the volume. There are 3 working groups in the IPCC. Okay? They're effectively split up by their tasks. Working group 1 is the quote, physical climate change, physics of climate change, what's causing it, what do we know, what do we see. Working group 2 is vulnerabilities, it's basically impacts, adaptation. What are people doing? What will be their response? What's the damage to agriculture? Social damage. Working group 3 are the technocrats. They're the economists and the technologists saying, oh, well, we can build this new technology if we only tax carbon so much. How much carbon CO2 emissions can we reduce and so on. So it's the economists and the technologists are in 3. A lot of the biosphere people and human impacts, agriculture, social systems will be at 2. And number 1 will be sort of the classic physical climate people of what can we measure for temperature, rainfall. And so that's been the split fairly well since the beginning and shuffling a bit in terms of what's going on. There's also a task force on greenhouse gas inventories. One of the things the Framework Convention requires is that Annex 1, the developed world, report greenhouse gas inventories on a regular basis. That has been very important because it starts establishing national reporting of what countries think they're emitting. This is good. Now, that said, it's under the IPCC, and the IPCC sets up the rules of how you report, what spreadsheets you use. If you're feeding 500 cattle, this kind of feed, it says what your methane emissions are per year. So it's like when you're doing national reporting, you go through all the inventories of all the various sectors that emit greenhouse gases and the rules for converting that to emissions in the countries you're supposed to report. 4th assessment report, 2007. We're going to spend most of the time, because that's the hardened stuff. There's new science along the way. Bits and pieces are coming online, and new assessments coming online, which you'll see also. This is the document we'll go through most pieces of because it's codified and written. Okay. Those are the 3 volumes. You see one in front of you that I brought with me. These are the other 3 volumes, group 1, 2, and 3. Okay. They're all about the same size. Okay. What is in an IPCC report? What does it look like? Okay. This is chapter 1 of that working group. Okay. This is the one I got to do last time. Chapter 1 is where they put the old people out to feed, to seed, so to speak, is where you move people onto chapter 1 because nothing important ever occurs in chapter 1. And I was laughing hysterically because I've seen chapter 1 for 3 assessments, and then when I got put into this assessment, I knew that my days were numbered. Okay. I've been put out farm. Okay, chapter 1, but this is like this is, for example, the references in chapter 1 go from what, page 100, you start at page 122, you've got about, each chapter probably has 500 references in it to the current literature and what's going on. So it's not just a review paper, but it's a paper reviewing the advances in science. You don't have to review every published paper. You have to review the ones you believe in, you think they're relevant to climate change. But needless to say, it's a very heavily documented piece of work. And quite heavily reviewed. It's not just a government, it's not a technical report that gets put out. See the process. This is the summary for policy. This is the beginning of the document. Actually, this is the front cover of the page. So if you look at this, we have our title page, and then we have all our chapters. This is working group 1. This will be the 1,000 pages you see in front of you. Chapter 1, historical overview. Again, chapter 1 was told that you couldn't talk about anything new in science. So we had to have a chapter based on everything from 2001 and before that was relevant to an assessment written in 2007. It's a very strange set of rules, but we tried. There are 11 chapters. There's a summary for policymakers and a technical summary. Technical summary was not always there, but they started using it more or less. It's basically an intermediary document where you gather material. It's useful for you to run through because in 90 pages you get some extractions from the underlying chapters that you would get. It's faster than reading 1,000 pages. But if you really want to look at something, the technical summary is this intermediate document. The chapters have the core material. They've written up, they've been reviewed, and then you have the summary for policymakers, which is meant to be the short document. and the technical summary lies somewhere in between. So it's a useful document for reading, but it's an odd document because you can't see governments using it, and you can't see scientists using it. You can see, somebody wants a quick read through, yes, but it's fairly tough, like 80 pages. It's a technical summary. So we're going to look at the summary for policymakers, and this is sort of the layout of it. We've got the governments told the scientists to do a 10-page summary for policymakers. Okay, so here's the summary for policymakers that finally got delivered for Working Group 1. Okay, here's the final one. This is the typeset one. This one came out of the government plenary, and we'll look at the contents of it in a minute. But here's the layout. You have the title page and whatever. You've got the middle one. You've got these big blue blocks that I've circled in red to show you this is sort of the headers. Then you have this sort of reddish-orange thing we'll look at. These are meant to be the major points here. Guys, they're not very easy to read. The typesetter did some bad choices, I think, compared to the previous one. They're hard to read. We have figures. This is page then 3 and 4. We've got some figures. We have text in little blocks. We have new headers. We have, under the red bulleted things, you see a series of small bullets which then bring up individual details. Okay, tables, some figures, okay, another set of figures, some final ones. And we're now down to 18 pages instead of 10. Okay, this is normal. Tell scientists to produce something 10 pages long, especially when you have 40 of them put in there. Now, the problem is you have a document that's that big, okay? Each chapter has written their own 100 pages, basically, 50 to 100 pages, okay? They then send somebody, usually represent the chapter, to the summary for policymakers. They want to make sure their chapter gets in because their chapter's been the most important, okay? And so then the usual problem comes is that then every chapter has to have something in the summary. I think chapter 1 gave up and we said, no, we don't really have to have something in the summary, but everybody else thought they had to. So if you actually look at this document, it's actually in the order of the chapters. It's not a summary. It literally is an abstract. It's pieces in the chapters in order. So my objection to these current documents is they're not summaries. They're really abstractions. They're no synthesis. It's a quick summary. I think just they pulled out the bullets from each chapter in order, and if you look at it, you sort of read every chapter has their section, which is okay, but it's not exactly, it's not inspiring in terms of the synthesis. So, and then everybody defends their little paragraph. So if we begin, let's go through the pieces of it, okay? It begins with, quote, human and natural drivers of climate change. Okay, and underneath that, which is the main bullet, so this is saying, what are we doing to change climate? What also changes climate that we don't do? So the other things change climate. Climate changes on its own without anybody knowing why. Okay, there's internal variability in the climate system, another problem, okay, that we don't understand. And so all of that has to be evaluated, and this one is trying to say, how do we know what actually forces climate? So it's issues of greenhouse gases, aerosols, land use change, things we know are changing the energy balance. We begin with a little chapeau, which is this italicized thing. It's not too inspiring. They weren't in the first draft. They started making them longer. And all this says is since the TAR, which is the third assessment report, you'll see a lot of TAR words. TAR is the third assessment report, and this is the fourth. You'll see a lot of words that say, new observations and so on have greatly improved our knowledge. Well, if it hadn't been, So this one is sort of a waste of space, but for some reason people liked it. I don't understand why. Then what happens is the first major summary of this section, okay? And so now you see probably the most important words that come out of this section that will be used, okay? And then if we read it, it says global atmospheric concentrations of carbon dioxide, methane, and nitrous oxide have increased markedly as a result of human activity since 1750. And then you go on and now far exceed pre-industrial values determined from ice cores spanning many thousands of years. That was a fight whether it was 300,000 years or 600,000 years, and people just said, just say many thousands of years, it's too complicated. Seriously, the issue is how far back does the ice core record go and how solid is it and what are the gaps on the ice core bubble issue. So that was sort of fights over tiny words to come out that you didn't need to be too technical at this level. And then it says global increases in CO2 are due primarily to fossil fuel land use change, while those in methane, nitrous oxide due to agriculture. This at least states what we think are the primary forcing agents, those big three greenhouse gases. It says roughly what they're due to, and it says they've changed well beyond sort of the historical record. So in that sense, it's a fairly good, clean summary of that's the section that follows, and we'll get details. Does that make sense? Now, again, we'll look at how those wordings get picked later when we see what the governments do to them when they try to read them and understand them, and what the scientists write in the first place. So under that, and I just highlighted various things, we have the bullets. So CO2 is the most important one. It gets top billing. What are the big issues on CO2 is the average growth rate. When I was first doing this in the 1980s, CO2 was increasing at 1.5 parts per million a year. Now it's almost up to an average of 2 parts per million a year. So the rate of increase is going up. It's not unexpected based on the models we have for carbon cycle, but the observations are fairly clear that it's sort of increasing even faster. It's consistent. We're putting out more every year. We keep burning more fossil fuels every year. This is not inconsistent with the picture we have. So it's nothing really unusual, but at least it's confirmation from what we anticipate from industrial activity when we know carbon cycle models. Then we deal with methane and talk about the methane increase. It's one of the gases that's changed the most since pre-industrial, from 700 to 1700 parts per billion. Okay. Now, all the gases are going to be done in parts per billion, which is the fraction that they occupy in the atmosphere by molecule count. Okay. And so methane is literally 1,700 parts per billion molecules of dry atmosphere. That's how it's measured. You measure it relative to O2, N2, and argon. You measure so you don't include water. Get the water out. You measure how many molecules you have of methane per molecule, say N2. That's the way it's measured. In the old days, people used to call this parts per million by volume because the air quality people had parts per million by mass. They'd actually collect it and weigh it. And it's not by volume, so people still go on because it actually is not a perfect gas. So you'll see a lot of stuff that says ppmv, but that's incorrect. Even National Academy reports came out recently this year. They keep calling it ppm, parts per million by volume. This is a pet peeve for the chemists because we've been trying to fix it. They don't understand what they're measuring, but anyhow. So, yeah.
So how reliable are the measurements from earlier, pre-industrial periods?
Let's look at, there's a figure coming up, and let's look at that one. Good point, so let me just there. And so then what's the backup on this? So if we go global industrial, then we have nitrous oxide, and then this is the figure trying to show the history of gases. Now, there was a better, I think this figure to me is very confusing, but let's at least see what's in there. Real estate's important. So the left-hand side is the page that we've got. We've got 14 pages, maybe 17 pages without introductory text and titles that are useful. So in this document, figures and tables are very expensive. They're prime real estate. They're the most used in seeing things. People read words. And so the choice of figures in these documents is absolutely critical. Okay, the fight to get a figure in or thrown out is really tight because you really have so much space, and the figures and tables are really very essential. Okay, we'll look at sort of what changed on those. You'll see no figure changes during evolution, but you see a lot of tables appear and disappear. This is the history of trace gases. Bottom figure is we have 10,000 years before present to now. Okay, the insert is the more applicable one, which goes from 1800 to present, or the little tiny inserts. Okay, and if you look at the inserts for CO2, for example, the red line are atmospheric measurements at Mauna Loa and sometimes South Pole. They're not global, but they're measurements at two places. They're representative of most of the globe, so we can actually have in situ atmospheric measurements that are reported for those gases. For methane, we don't have measurements that go that far back in the atmosphere, but we have them going back in old air to the 70s, basically, late 70s. Then we go to using ice cores and firn air. So we go basically to the air that sits in the compacted snow and in eventually closed off ice cores. Deep ice, about 10% of the volume is effectively gas bubbles. Okay? Not mass, but volume. Okay? So effectively, we have all these little bubbles that are trapped in ice cores, and that's why this goes back actually maybe 800,000 years now. In the Vostok core, you have numbers on these gases back 800,000 years. Now, how reliable are they? They're hard to measure. It's a great art form in science. It's tough to do. Okay, people do it. Eric Salzman does it here, for example, and other things. And people work on isotopes to find even that there are isotopic differences, shifts in these gases. So, but the ice cores, these gases do not photochemically react on the ice. They don't react with water very much. They don't react. There's not even when sunlight's on the ice. They don't react. They're fairly long-lived. So these gases are fairly stable. And so we see them being preserved. Other gases that we're interested in, like ozone, is not going to be preserved in the ice cores. It's going to react. So these are the nice long-lived. They're fairly inert. They have long residence times. The chemistry is fairly slow. These ones we got. So what you really see is this massive growth in the last 200 years, 150 years. And if you go back, what's not shown here, and we'll look at later, is if you go back further, you find that the period here, the last 5 to 10,000 years, is the high point for the last 800,000. The ice age cycles go back and forth, and what was the highest points are the interglacial warm periods, and that's like ours was 10,000 years ago. So we're way beyond the normal cycle of anything the planet's seen for probably about 2 to 3 million years. If you go back 10 million, 20 million years, there was higher CO2, we think. No ice cores, but we think, and there was different climate issues. But for the last probably 2 million years, we're well outside the current sort of ice age cycles. again, it's sort of, they had to blow it up because the figures on the right, how useful is the figure? The figure on the right, it goes, has this nice dip, for example, and then it just goes straight up, so you don't really get much information. So then you have to blow up the figure you want to see. And the question is, what's the more important figure? The fact telling people that what happened 5 to 10,000 years ago versus what happened in the last 200 years. It was their choice on what they wanted to do, what the authors put forward. The other one is that I cannot figure out the colors on these. This is a figure that all the colors are different, as you note. They mean they came from different sources. This is very good. But in some for policy level, this does not matter what the colors are. And so reading this figure is like a kaleidoscope. Okay, I really have no, and you just sort of ignore the colors and say, let's follow the lines. But the authors had very important, because this one came from this group who did this measurement. This one came from that group. It's very nice to identify where the sources were in the figure in the chapter. But at this level, it sort of doesn't matter. Next page we hit, which is the radiative forcing bar chart. So, given the gases have changed, what's the science of it? This one says that we've actually changed the radiative forcing of the planet. So the bullet here says, because we've changed the composition of the atmosphere, we think we have changed the warming. We've changed the planet by basically putting a greenhouse blanket on it effectively and warming it at a rate of so many watts per meter squared. Now, this is for the governments. The governments, this is their 4th assessment report. You don't need to explain watts per meter squared to them. So you have to go on the underlying chapters and say, what does it mean? Well, if you look at the underlying chapters and some of the frequently asked questions, the Earth is an energy balance system. The average sunlight coming in is 200 watts per meter squared, 140 is reflected, average around the globe, so you have 200 watts per meter squared that heats the Earth, and if you put an imbalance of about 2 watt, 1%, that's what we have now, and then the planet has to heat up to get rid of that extra 2 watts. So what we've got is an imbalance by greenhouse gases prevent radiation, they prevent the Earth from cooling, it's like a blanket, literally, and so what does the Earth do? It heats up, because it still has to cool. What comes in goes out. You have to get it out. And so what the trapping does is measured as an imbalance in the radiation. So greenhouse gases and aerosols and everything else will be given as watts per meter squared. For some of you all, this is a shock. I mean, it's a sort of new issue, but for the government, you'd say to the government's no, they've been seeing this for 15 years in the last assessments. So this is not news to them. Believe it or not, people high up in the State Department know exactly how many watts per meter squared are important. Okay, they're used to that. That said, so that's why there's not a lot of explanation here about this part. Okay. And you'll look at, now we actually have uncertainty ranges. It says 1.6 from 0.6 to 2.4. That's new. 2001, we did our best guess on the numbers. Now the new assessment actually has estimates of uncertainties. And this now brings up the other gases. It says we actually look at the big gases, carbon dioxide, methane, and nitrous oxide. We have almost 2.5 watts per meter squared. Those are well known. And then we have cooling from aerosols. And then we have the contribution from aerosols, our negative cooling. And then if we look at the big chart here, this is sort of a summary chart of what are the things we're doing to kick the climate. Okay. It's done on a very coarse scale. It's not regional, it's global. It's really putting the pieces together of what are the main players in the game. And so, for example, the governments insist on having aircraft in there, because aircraft were a big assessment on climate in 1999. And it's a very hot topic. The public is very convinced that aircraft are causing major climate change. And so they put aircraft in there, linear contrails, because CO2 from aircraft is equally small, just to show that it's sort of sitting, like that big. Okay? There's no reason to put it in there, but I think politically somebody wanted it in there because to demonstrate it was not a problem. Okay. So this puts the gases up, it sort of ranks them. The red's warm, right side's warming, left side's cooling. We see the major greenhouse gases. We have ozone in the middle from the stratosphere to the troposphere, which acts as a greenhouse gas. We have aerosols, which both cool the planet and also change clouds. The big thing is the aerosol indirect effect. Aerosols tweak clouds, and aerosols enhance the cooling of clouds when they interact. So they basically make clouds brighter and whiter, so that aerosols have double the impact in most places because of their direct effect is scattering back sunlight, so they cool the planet, and they also impact clouds. And that's the hard part. That one's a very tough calculation, has large uncertainty. If you look at the bottom bars for the aerosols, much bigger error bars on the aerosols than there are the greenhouse gases. Okay, it's a tougher one to do. So we have heating for greenhouse gases, cooling for aerosols, okay. And then we get down to this thing, which for the first time ever, they actually tried to figure out what is our best number, what's the assessment, what's the uncertainty range, which again was not done. Last time we said we know we're warming, but we're not sure why. This one actually tries to combine the uncertainties and the ranges using both forward models and inverse. We know what the climate's done for the last 50 years. We know sort of how we've been heating and cooling. If there's some uncertainty on what it could be, So you can constrain all sorts of things from observations as well as from the modeling. And this is the best estimate of that we are warming, and it's sort of between 0.5 and 2.5. Okay. Yeah.
Is the cooling a good or an offset to the
Yeah.
heating?
Okay, yeah, and that's why it's that side, and that's, yeah, in theory, if we put enough aerosols up, which is one of the geoengineering ones, we can cool the planet and balance the CO2.
Yeah.
Now, that said, if you look in the underlying chapters, are these additive? They're plotted on the same units. They're all watts per meter squared. So the assumption is you can add them up. They have the same units. You put the bars on them. Okay. If you look in 2001, the same bar chart, it looks the same. Actually, it's rotated differently. It's very funny. All the bar charts to 2001 were horizontal, and then the bars went up and down like this, and they had species underneath them. This group decided they're going to be clever and rotated, which I think is dumb because you're dealing with governments and they're used to seeing a certain figure, they love to deal with it, and being cute, scientific, saying, oh, we have to come up with a new way to show it. I don't think was actually that good an idea. It's okay, everybody has to sort of look like this. But that said, these now can be added. If you go to 2001, we tried to add them once in the synthesis report. I was doing the synthesis in 2001. We had the bar chart. I added them up. And authors complained and noted in their figure caption, the figure caption in 2001 is as large as the figure. It says you can't add the numbers up. I said, well, why'd you plot them on the same units? Well, yeah, but we can't add them up. This time, same old authors, they got together, they said, we have to add them up, and they agreed to add them up. Thank heavens. Because early in 2001, they said, here are the individuals, they're plotted, they have the same units, but you can't add them. So, aerosols cool, they all set the heating. The difference is aerosols and solar and whatever which are there have slightly different climate effects, but within 10 to 20%, they add. I mean, some of them have slightly different pushes on the climate, maybe some are slightly more efficient and less based on this unit, but the best numbers we have say in first order, add this up, you may be off by 10, 20% on any individual one. What it actually does to climate. That is, it might take 1.1 watts of offset of aerosols to offset 1 watt of CO2. This is the relative efficiency. That's where we're.
Are there interaction effects?
There are, but that gets to be even more complex. These are just because aerosols push it by cooling low down. CO2 heats the upper troposphere, so they have different effects on clouds. They sometimes change lapse rate a little bit, so they change some of the other effects. So they all drive the climate imbalance, but the response of the atmosphere and weather can be just slightly different. Anyhow, this one, they added them up. This is important. This is a very important figure because it has all the pieces. It reminds you of all of them. Okay. The solar irradiance was a big issue. It's now smaller. Okay. It's been reduced. Nobody really knows what the sun was. They scale to sunspots, but that's not necessarily scaling to the amount of radiance coming out of the sun. We only know this radiance from the sun from satellites in '79, where we actually put stuff out in space and measured the heat coming literally through a pinhole. And so trying to measure the changes in the sun going back in time are really hypothetical. It's like going back beyond when you have ice age. Ice core data for greenhouse gas, you really had no information. You sort of guess back on other things. Again, this one now, you have the summary about the total, which is impressive. Okay. So now that says what we think is doing it. It sums up the pieces. It says the relative size, what the problem is, and now we're going to look at what has the climate changed or not. So our next piece is, what's happened with climate change. So we have direct observations of recent climate change. And so this one is the favorite of the co-chair who did it. She was very proud of the warming of the climate system is unequivocal, as now evident from observations of increases in global average air and ocean temperatures, widespread melting of snow, global average, and sea level. Okay. The unequivocal part means that there are more and more things that look like a warming world, as opposed to just the global mean temperature going up. So these are other things that if the world were warming slowly on average, you should be seeing these other changes. And that's sort of the one thing is we see more and more pieces that are consistent. Okay. So what are the headlines? This one I don't like. 11 of the last 12 years. When they first wrote this, they didn't put the years. And so it's very interesting when you're reading a document that might be 5 years old and it says 11 of the last 12 years, you're trying to figure out what it was. And so one of the complaints in the reviews was to put the years in it just to remind people because documents should be dated. Okay, the 12, rank among the 12 warmest, okay. It's a very interesting statement, but it's also subject to some uncertainty because actually the warmest year involves things like different groups will be off by 0.02 degrees on one year or the other, and that might shift the warmest to another time. It's not a robust number. This is not a really good statistical number. It's a catchy one, but it's not robust. So if somebody else reanalyzed the global temperature data, it might be 10. That's what you're saying. So, it's not one of the tougher numbers, but a large number. It has been warm, but it's no question. Okay. This one is the new analysis of the balloon measurement. One of the big things from our friends down in Huntsville was they analyzed the satellite and said, oh, the upper atmosphere is not warming. That is about 8 to 10 kilometers. We see satellite measurements. We had them for 30 years. It's not warming. There's something wrong with the whole greenhouse effect. So finally, there was major work to reanalyze the satellite data, to look for errors, look for systematic biases. And I would say 5 out of 6 groups analyzing the data independently all come to the conclusion that the upper troposphere is warming. Christie and Spencer, the original people, still disagree. They think it's cooling, but they're the only ones who use the same data set and get cooling consistently. So people sort of given up on their stuff, and moved on. But that was a big issue up until this time. Okay, in 2001, that was a big fight as to whether or not whether it's sensible the upper troposphere should be warming. It wasn't. This one shows that the ocean. This is probably the biggest thing that's new. It's important. The heat's going in the ocean. This is a major issue because it's fundamental. It has to go into the ocean. It's the only place it can go. It has to go in the ocean because there's no other place. Okay. You cannot absorb enough heat that we are putting in balance in the atmosphere. It's too thin. It doesn't have enough specific heat. You can't put it in melting glaciers. That's not enough to take the heat up. The only place the heat can really go, it's got to be in the ocean. So we have an imbalance in terms of heating the globe up. We've got to be heating the oceans up and then heating the planet up to get the imbalance out. So right now, we're not in balance, so we have to be pumping heat in the oceans, and this is the new results, which basically from the oceanic surveys show that at least the upper ocean, we have clear evidence of warming, top, say, 700, 800 meters. Mountain glaciers declined. Losses of ice sheets in Greenland have likely contributed to sea level rise. We'll start seeing likely. We'll look at the uncertainty issues. This global sea level rise is a very hot topic. There were a lot of problems with sea level rise in this report because sea level was dealt with in 3 different chapters and they didn't get together in the summary. So the first draft of the summary has somewhat disconnected. There was the historical, there was the current rate, then there was the future projections, and they all sort of had discontinuities. They're all not necessarily consistent because each chapter sort of did their own thing. And so one of the problems with the SPM summary was it didn't really pull it together that well, so there's a lot of juggling near the end to squeeze this in. And so this one is, we have sea level rise from 1960, that's from tide gauge data. Okay, tide gauges are notoriously chancy because land moves up and down because of glaciers and other things, and so you have to take that into account when you have tide gauge data. For a given station for 40 years, there's motion of crust everywhere, sea level rise. Also, tide gauge data is not everywhere. It's only in a few stable ports. So you have long-term measurements. Satellite data came online, was it 93 basically? That gave us a global measure of sea level rise accurately, which then can be extrapolated back. They're arguing that the rates are somewhat consistent and they may have changed. So this is the period we've got it for. Another big figure, whole page, is this three-part thing which deals with, let's look at it here. This one I don't like particularly, but this has global average temperatures, global average sea level, and then northern hemisphere snow cover. So they decided they wanted to show time history of some climate change issues. And so they're a little bit odd. I mean, the first 2 are major global ones. They're sort of fairly well determined. The bottom one is basically northern hemisphere and Siberia, and snow cover change. And it's hard to get snow cover when you go back beyond the satellite era, because you have to have people out there saying how far was the snow edge and what was the area. Satellites, you can get snow cover pretty well. But once again, the snow cover one doesn't show, shows a funny shift, 1990, but it's not clearly a general global warming one. The sea level and whatever else are there. The little red tongue they put in at the end of the snake is my question mark there. I love that for some reason. They decided to plot the sea level rise and then put the satellite data in the end. It's just a very strange figure. And it's huge. This is a whole page of, this takes up a whole page. And the question is, my question is, do what you get out of it or not? But they were trying to show 3 different things that were changing in terms of climate. Next, we get more details in the table. So this is regional scales, what's happening in small scales.
Great question.
Yeah.
Could you go back to first?
Oh, this
I just noticed a blip in the top one.
Yeah.
About late 40s.
Yeah.
And then for the temperature, and then it kind of drops back.
Yeah. That's a funny period. If we get to it, I'll talk about it later because we have some issues on predictability as to whether that's predictable. That's one of the epochs, the 1930s and 40s. The warming started in the 30s. It warmed again in the 40s and then dropped back down in the 50s. That period is not predictable by the climate models. Something happened to the climate system that we don't know, that we put in everything we know, and most models all miss that. And we'll see it when we look at sort of 200 years of temperature predictions from the models, and you'll see that little blip on the Earth's thing. That was it. The other thing is, it's a very weird thing. It's North Atlantic only. It's almost entirely North Atlantic. Globally, it was huge on average, but it's almost all the North Atlantic. It's basically between US, Europe, and the North Atlantic, and then spreads a bit. It doesn't look like the current pattern of warming. If you look at the structure, and that one is totally different than the current structure. And so most people think it's the North Atlantic. There's something that happened in the ocean, in the Atlantic, some oscillation that went through the system that stopped, basically it warmed, it stopped deep water formation, you know, basically stopped putting heat down, so it just warmed immensely up there. Nobody knows quite why. It was a surge of non-saline water that sits on the top. Who knows what did it, but something odd happened in the North Atlantic in that period. And that's sort of, if you want to say that's one of the holy grails, if somebody can come up with a climate model and tweak it in a way that does it, that'll be nice. That'll be a well-awarded paper.
Wouldn't be nuclear testing.
No, it's too big. Nuclear test, I mean, this is a huge event for the energy system. And nobody knows how you can force it with any of the forcings we have. If you tweak any of the forcings, aerosols, anything, they're just not big enough to push that blip that quickly. So it's something internal to the climate system. And the climate does bounce around, so it's not unusual. This one again, continental scales, we look at regional. Arctic sea ice has shrunk, gotten thinner. Let's see, permafrost layers melting everywhere. It's receding back, so we're losing the permafrost in the high north. That's important for building structures, as well as potentially release of methane and carbon dioxide from frozen soils. When they dry out, they're going to basically oxidize. This one is precipitation. We've actually seen precipitation trends. Precipitation is the hardest thing to get trends in because it's very small scale. Okay, we can measure precipitation here in the airport and we'll get different numbers. We have to measure 20 years to get the same precipitation here in the airport to get close enough numbers because it really comes in small scales. Unlike temperature, which is fairly broad scale. Okay, and the correlation distance for temperature, I think, is several hundred kilometers. If you look at variability in temperature, if you look at precipitation, it's probably no more than 10 kilometers. Try to remember the sort of correlation lengths. So the number of stations you need to do precipitation will be very tight. We don't have them, rain stations. But long enough time period, you do enough statistics, start seeing things. So we do see trends in precipitation. Yeah, there are in there. Not everywhere, but they're there. So this one now talks about the big table, is observed rate of sea level rise. This was important because sea level rise is still a major concern, smaller than the States, everything else, and it seems to be the inexorable, sort of the inevitable. One of the things about climate change that's going to happen is the glaciers, the permanent ice caps, Greenland and Arctic, are going to melt enough to push the sea level up at some level. The question is how much. So this became a hot topic, and you can see that this list is interesting because if you look today, glaciers and ice caps are the small ones, okay? And they contribute a fair amount to sea level rise, okay? But they're almost gone now. I mean, they won't be doing much in 30 years to sea level rise. We've lost a lot of them. Now it's Greenland and Antarctica. The big thing up there is thermal expansion. The first one's thermal expansion. It's also called steric. What happens when you heat ocean water is it expands. So as we pump heat into the ocean gets bigger and bigger. That's half of sea level rise basically is the thermal expansion. Okay, and that's fairly well known. That one the models do a reasonable job of doing. So when we look at projections of sea level rise, this thermal expansion, the atmosphere ocean models will be predicting the heat going to the ocean, the heat going to the atmosphere, they'll predict the expansion. What's hard for them to predict, because we don't have good models, is the glaciers. Greenland and Antarctica, what's going to happen to the water there, that's much tougher. Okay? And so that's the one where there'll be disagreement. So what happened was this group punted on the Greenland and Antarctica problem. Historically, they noted what they contributed, but the future, they sort of said, well, let's assume it's the same, it doesn't change much. Because they didn't have any background, they didn't have the models, and they didn't include that much in the uncertainty. And that was the major objection, was that the projections of sea level out of this document are lowballed because they include thermal expansion, which is going to happen, that's pretty reliable, but they don't include any additional melt from Greenland and Antarctica. Okay, other bits and pieces, westerly wind strengthening, more intense droughts, these are the issues, frequency of heavy precipitation increased, changes in temperature extremes. The third one's interesting. This one is actually one of the few precip ones that's really robust. It was even robust in 2001, it's even tighter now. More precipitation is coming, even in places that are getting less precipitation. More fraction of it's coming in the heavy rainfall events. This has to do with culverts, stability issues, how you capture water for drinking, everything else. You're getting less drizzle and less low-level, consistent low-level rain. You're losing the drizzle, and you're getting more extreme events. So even in places that are drying out, you're getting more extreme rainfall. You're getting the rain condensed to fewer days. And the events will actually be more intense, even if there's less rainfall on average. So this seems to be pretty robust, and even the models get it. I don't understand why, but this seems to be a fairly reliable result of a warmer, wetter atmosphere, which is what's happening. And it does seem to come out both in the models and the measurements. Okay, if you want to say, is Southern California get more or less rain, the models won't agree on that one. Okay, and even the historical data is not always clear. Certain areas are drier, some not. But if you want to say, is it becoming more and more extreme events, the answer seems to be robustly yes. Interesting. And we have a little table here, which is very confusing to me. If you look at this table, I didn't do it, did I? I didn't bother blowing this one up. This is a table of what extreme events, little events, warmer, wetter days, and whatever. This is sort of the blow up of, are they becoming less likely, more likely? Do we think what's going to happen in the future? Most of these things are fairly low likelihood. So, for example, what's the likelihood of the human contribution to increase incidence of extreme high sea level is more likely than not. It's not a convincing argument that it's more likely than not or less likely than not. They picked all these little events that have great human impact, but those events are very hard to attribute to human climate change right now because they're all regional, they're all fairly small scale, the models are not robust in predicting them. But what they didn't put on this table was the things that, is the world going to get warmer an average of 0.1 degrees per Celsius per decade? That's probably extremely likely based on what everybody would say. They didn't put the high likelihood ones at the top, they listed all the little ones. And so I think they could have done a little better job on this one. Paleo has their own section. Again, this is an example of how paleoclimate has their own section, of how every chapter basically put their stuff in order. Because the paleoclimate would be most useful if it was used to support the arguments for all the other pieces. And what they did was they just wrote up the summary of their chapter. Okay? And so some of the aspects, okay, so we have these bullets here, some aspects not changed. This is the only one example that we have, I think there are a few others, but hardly any, where we haven't seen climate change. And one of the things, that's the Antarctic sea ice extent in Antarctica. There just doesn't seem to be any obvious trend or pattern in sea ice. Well, A, it's very cold, hasn't changed that much, okay? It's one of the big, slugs in climate warming is Antarctica. You have circumpolar currents, deep cold water, you've got a huge 3 kilometers of ice, okay? It's a cold place, and it's going to be a while before it warms. That said, it'd be nice to have some other examples, because I'm sure there are cases where things have not warmed, and not everything is just this constant uniform increase. So the paleo one has their favorite, one of which is this 4 to 6 meters of sea level. Okay, and that is going back in time 110,000 years ago, there was a warm period like we had now. Greenhouse gases were like what they were 5,000 years ago, not what they are now. So they were the typical warm interglacial period 110,000 years ago called the Eemian. It was warmer. It was 2 to 3 degrees warmer than it is now. Okay, partly because of orbital issues and whatever. Okay, the orbit was slightly different. The greenhouse gases were not what they are today. They were literally 1,000 years ago. Yet that period was very long and it warmed. And so there was a sustained slow increase in warming, and basically from corals and whatever, you have sea level rise being 4 to 6 meters higher than it is now. Okay, and so we're looking on a long-term ability to exceed that, because unless something else happens, like we pull greenhouse gases out or whatever, it was not that much warmer. But it had maybe 1,000 to 2,000 years of warmth to do it. So if we maintain our current warmth and keep going with greenhouse gases, people predict most of Greenland will melt like this, 4 to 6 meters, in a time frame of 1,000 years. The real issue for climate change is 1,000 years is very long politically, and even for a nation's sort of sovereignty issues. But people are worried about this happening in 100 years or less. And that's sort of the rate of change is the key issue here. Let's see, on reduction, now that's repeated, okay. Mostly observed temperature is very likely due. This is one of the key attribution ones. We'll look at what the evidence for it is, that we think the increase since the 50s is greenhouse gases. Sort of a wide range of evidence for it, tests. And part of it is you put the best models in, you put the physics in, and you get the result. And then the other is you go back and tweak the models and say, well, suppose we're off a little bit here, suppose we're off a little bit there, we have uncertainty, you try again, you still get the answer result. And then you say, is there any other possible idea that people have come up with? And the answer is no. People propose it, people test it, and it fails. So in general, it's a fairly likely issue that the increase we see can only be explained by greenhouse gases, only forced by that. Now, there's 2 likelihoods. This is very likely it's greenhouse gases, and we caused it. Okay, that's the top one. The bottom one is it's extremely unlikely that it can be explained by natural climate variability. So if we look at the last 50 years, it does not look like any natural climate variability we've seen. Now, the next question is, was it human-caused, or could it have been a bit of the sun? Could some of the CO2 have been due to other than fossil fuel? Yes, that's why you go from an extremely likely or unlikely to a very likely. So one of which says, there's no way that we know the variability of the climate system doing that. And the other says that, one notch down, what caused it? We'll look at the picture in a moment. Do we have that? No, we don't have that here. Warming climate systems detected in the upper of the ocean, okay? Warming over the last 50 years except Antarctica. This is the attribution figure, okay? So what we have, if you look at this one, this is the sort of the new one. The last time there was a global picture. This is continent by continent, and then the oceans are some below and land some below. So the black line is the Earth's climate history. And then the pink line are all the models that are run with greenhouse gases, and the blue line is all the models that run with everything but greenhouse gases, basically, and aerosols, the sort of anthropogenic part removed. And so what you see is in the last, so many years, now the annual average is done sort of decade to decade, so the Earth history is very chunky because they didn't do year to year like they did before. They're running for decadal averages. But in general, you see that the pink lines, the pink band and the black line coincide, and the blue lines basically have gone very far away from. So we think we're way out of any of the natural systems. Okay. The most intriguing on this is that it's continent by continent, so we're getting down to not just global means. It was done before for global means. This is now looking regions, and there are differences in the regions. The interesting part is the differences are consistently predicted. The higher north latitudes are changing much faster. They're predicted to change much faster. Okay. And so again, confidence and predictability. Yeah.
Do you know how come the north is changing quicker than the south?
Yep. Basically, there are many things that go into it. As you go in the tropics, it's a big heat engine. You slowly heat it up. There's a lot of energy in the tropics in the first place, okay? So putting in greenhouse gases warms it a bit. It does warm a bit, okay? When you go to the high north, you have land, not ocean. Land has no thermal inertia. The heat from the sun every year, seasonally, does not go very far into the soil, okay? It does not really take much to heat up the land. So what greenhouse gases are predicted to do is greatly increase over Siberia and northern Canada, the temperatures there. And that's what's seen. In Antarctica, you don't have land, you have ice. And around that ice in Antarctica, at 60, 55, 60, you have a circumpolar current, which is a rapidly moving current that actually goes way deep down and mixes. So you have very cold, deep ocean constantly being brought up all the time. It's a huge thermal inertia system. And so it's really hard to warm there. You can warm places in Antarctica like the Palmer Peninsula that sticks out by Argentina. That seems to be warming, but not many other places in Antarctica. Now, your question, the key one is this one. Here's the 1940s, 30s and 40s rise. And again, just sticks out, doesn't fit, okay? So here's what did it. Once again, it's interesting. It's a great puzzle. That's the fun one. I think there are lots of people playing with that one, trying to figure out how they can get a climate model to sort of have the climate burp in that way. But again, there are patterns to that one.
The Dust Bowls of the 30s?
Well, they could be related, but people played with that. They worked with that. People tried different things. But it's, the Dust Bowls in this may be related. They're probably related. But are they the cause or not, and what did the climate choose to, if you did a Dust Bowl, would you get this, or is this because you heated up in the first place? Various people have tried to play games with that. It's quite interesting. Projection of future climate change you end with, okay. Analysis, this one put a question mark. Analysis of climate models together with constraints from observations enables an assessed likely range to be given for climate sensitivity for the first time that provides increased confidence in the understanding of climate system response to radiative forcing. I just picked this one out because I laughed hysterically. This is one of the big, the big bullet to the left is before we get to future. This is the past one. It's big on the upper left of that figure. So it's actually one of the highlighted bold things. And I just don't understand how the governments could read this and go, what are you talking about? Because every time I read this cold, and even knowing climate science, it just doesn't sound, it sounds so convoluted. If you're reading it, I don't presume that you can make much out of it either, not knowing. But even knowing it, this one is not one of the more enlightened sentences that made it through the bullet section. So I can read through. I know what they're talking about, but they made it very painful. So this is a case where maybe the scientists did it, maybe the governments did it, who knows, but we'll see what happens. And then we get to more, the details are usually fairly clean. Unlikely it changes 7 centuries prior to 1950 due to variability of climate systems, significant fraction of our atmosphere. It's very likely attributable to volcanic eruptions. It brings up volcanoes have caused climate variability. We measure that, okay. And then this is for the next 2 decades, you predict about 0.2 degrees warming, no matter what we do. So this says independent scenarios. It says for a range of SRES emission scenarios, these are the different projections of what we're doing for greenhouse gases. There's a better table that comes up inside the document, but this really says that we're going to get warming of 0.2 degrees in the next 2 decades, no matter what, maybe 0.25 Celsius. Okay, it doesn't matter what scenario we pick. This one's fairly sort of written in stone because the scenarios can't change that much and the climate system can't change that rapidly. And then we have a little table down here. Let's see, the continuous greenhouse gas emissions cause further warming. This is one of the no-does statements. I mean, if it didn't cause further warming, we'd wonder if we continued to pump greenhouse gases in the atmosphere, then what's wrong with the system? But I guess it needed to be stated. Warming trends reduce the land ocean uptake of CO2. This is the beginning of the feedback issue. What's happening when the climate system changes to the things we worry about? This is one of the big worries. Saying, if the oceans and land suddenly get warmer, they are likely to take up less of the CO2 that we burn fossil fuels. That means more will stay in the atmosphere for longer. That means the CO2 will rise faster, and that's an acceleration of climate change. So these are positive feedbacks on the climate system, okay, through biogeochemical cycles. This is one of the hot topics. This is coming out in the last decade. There'll be more requirement for current. This is one of the issues of what does climate change do in terms of the feedbacks. This is not people's choice. This is saying, if we emit more CO2, the place heats up, we're going to have trouble getting rid of it, and so we'll actually have more in the atmosphere. The big table here is the scenarios. This says temperature range. It has different scenarios. It has the sea level rise. So the government, this is sort of the table. These are all the different optional scenarios that were done in 1998 that the IPCC sponsored and set up scenarios saying what are different futures likely to look like. So they ran a bunch of scenarios and just labeled them A, B, and just break down what these are. Read a whole page on them at the end. There's a block there. But this one, let's see, A2 is one of the high growth scenarios. It has the, for CO2 and weather, it has 3.4 degrees by the end of the century. And I believe it was B1. So A1's the top one and B1's the slowest one. So B1 predicts a lot of the greenhouse gases stabilizing due to technology and other issues. So there are different sort of future socioeconomic futures. Okay, and then the physical climate people evaluate them by saying, okay, given these scenarios for emissions, here's what's going to happen. And so these have been around since about 1999. They were done, the same scenarios were done in the 2001 report, and they were done in this report also. Here's the future figure. Okay, we've got models include feedbacks, uncertainties, and so on. Include, so they're warning you that we're still missing a lot of pieces in these models. And that's sort of a fairly important caveat. It's sort of hidden away in the bottom bullet. There's one of the little bullets in here, but it's a fairly important statement. CO2 feedbacks, having acidification of the oceans and other problems. So more than climate, CO2 acidifies the ocean because it forms, basically you put in CO2, it dissolves and it forms more bicarbonate, dissolves calcium carbonate, and you basically lower the pH from 8 to the ocean to make it more and more acidic. This is an ongoing problem. It's a high risk. It's been raised probably more earlier than this report, but it's now in the current report now, but there was not a lot of work done. So once again, there were a few papers coming out in 2004 and 2005 on this topic. They were very hot topics, but there are not a lot of studies done on what happens to a consistent thing. So you can easily show, there are a lot of papers that show I take a given coral, single species, and I up the acidity and the coral dies. They don't say what comes in to replace it. And so the whole issue is what happens to ecosystems. You know, any given animal is in its niche. If you twist the if you basically change the climate of the system, anything from the trees that grow there to the coral that grows there will shift. And the question is, will you wipe out all the coral and get brown slime, or will you have other species picking up the niche? Those studies really haven't been done. And that's the tough part. The complex systems are hard to do. This is the figure of what's going to happen in the future. We have the historical one, then we have the year of break at 2000, and then we have the spin-up of different scenarios. And there are error bars on the right, and estimate of what the range would be under those scenarios. You can see that. The right represents our uncertainty in the climate system. The different colors represent uncertainty in the socioeconomic system of different pathways. So those are different projections of socioeconomic behavior, the colored lines, basically. And the models sort of have, these are the general circulation models run for different ranges, and so that's sort of the range, maybe 40 or 50 model simulations. It's not a true uncertainty, it's just a model range. It's that large variance. And then what you get on the right is the estimate of combining the model range, plus we know the models have more uncertainty. That's what the big gray bars are. What do we think, say, the 90% confidence intervals are for the temperature range if we were to follow that scenario? So it involves issues of how well do we predict CO2 under that scenario. It involves how much ice melts back, what are the feedbacks, and everything else. So this is simply the range of models. And then this includes other information and knowledge we have about how the models could have other problems we don't know about. It's just based on paleoclimate, based on other analysis and parametric studies. And then this one is the last interesting big picture, which is fun. This is the projections of surface temperatures. This is an interesting and complex figure, and it tells a long tale. Whether or not it works, I don't know, but from the science point of view, it's great. There are three scenarios. So the three rows are the different scenarios. So pick one or the other, it doesn't matter what you look at. Okay? And then what you have is the 2020s and the 2090s. Okay? This is the climate models. Every year is variable. Climate has a large interannual variability. So when you look at climate projections, when you're running the full climate model, you always use a decade average. That's why this looks at the 2090s. When you were doing this more than 10 years ago, we just picked 2100 and say, oh, here's the rough answer at 2100. Now people are more careful. They actually have model results for the last decade of the century, so we'll be doing that decadal average. So you have the patterns of warming on the right. You actually have the geographic patterns, and you can see that even in the 2020s, there's still some cooling or barely half a degree warming around Antarctica. You see maybe certainly the light green colors down there, and then there's maybe a bit of blue occasion where there might be cooling, but not much warming around Antarctica, and the warming starts up in the high north. By the time you hit the 2090s, there's even warming in Antarctica, but the warming, which is not that large, maybe only 3 degrees global warming, you already have warming of 7 to 8 degrees Celsius in the high north. It's huge amplified warming as you go further north. The patterns you can see are not uniform. These are the average model results. And then on the right, you have a probability distribution. This is, again, fairly new for this assessment. You're going to see more of the next one. These are the likelihood of what it's going to be. So several models estimated what the global mean temperature was going to be in 2090s. And you can see they said, well, there's a range here and range here. And one model said, well, you know, sort of a long, wide range. Could be anything from 1 degree to 8 degrees. Okay. Every model did their best job of estimating how certain their numbers were, what uncertainties they could put in to give the range. The key thing about this one is if you look at the 2030s, which is the light orange, 2020s, and you look at the 2090s, the width expands greatly. Okay? It becomes asymmetric towards the top end. Why? In the 2020s, climate change has not been so great that we do not have examples in the last 100 years or even the last ice ages to calibrate the models and to say, no, you can only have feedback of a certain amount, because we have climate data from both ice ages and we have climate data from the last 50 years, or 150 years, that we can use to calibrate the models and say, well, you really don't have so much of a response to warming, and that's the uncertainty of the feedbacks. Once we get to 2100, we're in a world we have no information on, we have no calibration. Things are happening in the high north. By 2100, there'll be no sea ice in the Arctic in the summer. In winter, it'll reform. It'll be very thin ice in winter. In summer, it'll be totally open. There's going to be algae up there. There's going to be things growing up there. What's the feedback going to be on the carbon cycle? Okay. These things people have in their models, but there's no way to calibrate. There's no test. We have no observation of the relevant climate that we're moving into. And so that's why the uncertainty gets much larger. So this is one of the issues as we go beyond 2050 that we're going to a world that we have less experience of, and it's going to be far more difficult to predict. Okay, let's zip through this one. About that. Is there anything else really relevant? Higher confidence warming regional patterns. Okay. Based on models, likely future. This was one hot topic. And the future was the cyclones. It was all over the place. The sea level was a problem with this, and also with the cyclones, because there were early papers saying it's going to have more tropical cyclones and hurricanes effectively because it's a warming world. Then people started looking at it going, well, yeah, but if the wind shear picks up, you'll have less tropical cyclones, even in a warming world. But everybody agreed that if the oceans were warmer to a greater depth, you would have more intense hurricanes if you had them. And so it's back and forth on what really can we conclude. And over this period, starting in 2004 and 5, is when the first papers came out and said a warming world will have more hurricanes. And then people said, well, maybe not. But if they are, they're going to be stronger. And so it oscillated back and forth. This final rewrite on hurricanes and tropical cyclones was the one that bounced around during the whole process of writing, and even up to the last, February 2007, when this was finally written up exactly. So this was one of the tough ones. And it had obviously a very hot topic. People in the Caribbean, people worry about this, Southeast Asia. Okay. So this was certainly a hot topic, not predicting what was going to happen. So anything else on this one? Precipitation's tough. Okay, we'll get through this. This is precipitation. What did they show for the science? This is multi-model for different scenarios. This is A1B scenario. It's different seasons. projected precip changes. The only thing that's relevant on this is it's tough to do it. The colors give you the average. Brown is drier, blue is wetter, okay? It's the changes in precip of the models. And I'm trying to figure out what period this is. 2090s versus the 2 decades, lovely. 1 decade at the end of the century, it's about a 100-year change. The stippled area is where the models agree in the sign of the change. Not the magnitude of the change, if I'm not mistaken. The stippled area is where they actually agree in the sign. More than 67% of the models agree on the sign. So most of these areas, different models don't even have the same agreement on the sign. And so the stippled area was an attempt to show you where it was fairly robust, meaning that most of the models could agree that it was going to go up in that time. Then they'd average the results. So it's a fairly interesting pattern. It's not exactly robust, but it sort of hints at things. And you're probably going to see a lot better work on it. Hopefully it gets better in the next assessment. But this is one of the tough areas to predict rainfall. So I like the concept of stippling, because that would at least show something and say where they thought at least they agreed on the sign. It wasn't there within 1 sigma of each other. So, and then we have various other things about future ice flows. Greenland ice sheet continue to contribute to sea level. Okay. And we have our last box. This is the scenarios described. This is 1999 stuff, but they put a box in to remind people if they want to read up what scenario A1, A2 was, and so on. And that was the end of it. Okay. So remember what you guys to try to condense everything into 900 pages into those 14, or not everything, but the most important things. Okay, let's do a pause. Okay, we'll do a break and then we'll go. This is the technical summary, which we have on the lectures. Okay, so give you what's my take-home message from the R4? I've got about 5 slides here, which are great fun. Okay, okay. So I have 2 prophets. Okay, Ecclesiastes and Bob Dylan. Okay, for everything there's a season, but times they were changing. So this is freeze dates and thaw dates of rivers, basically. It's just seasonal stuff. You can see everywhere, basically, the Red River freezes dates getting later and later. It's just shifting down the year. The thaw dates coming earlier and earlier. You can see the season shifting on the freeze-thaw rivers. This is something I have a nice hard record on. People have been living there for a long time. It's one of the more solid ones. The other is more statistical. You can see sort of leaf unfolding and fruiting and other issues are all shifting to a warmer world. Not everything is. Some events and some ecosystems are shifting to longer and colder seasons, others shifting to warmer, but if you look at the statistics, you see more red than blue. That's sort of averaging over enough systems, so you're really seeing the season shift, okay? My favorite is the wine one, okay? The Rhine wine has gone up about 2% in alcohol because it's warmer and wetter. They're now growing Pinot Noir down by Frankfurt, okay? It's really quite good. The whole wine season in Central Europe has changed. It's really amazing. The other one to look at that's interesting is climate predictions. This one's relevant for what you're thinking, maybe you're thinking. Climate normals. Climate normals are the statistics. The statistics which we live by. So climate normals are a 30-year average of the weather. And then you say, okay, the next decade should look like the last 30-year average of the weather. And this includes everything, okay? Temperatures, heating, cooling, freeze thaws, precipitation, flood line, all the sorts of classic things that it's true. Climate is 30-year average of weather. Okay? Everybody's supposed to do it every 10 years. It's been updated recently. Tom Carl did this recently, and he looked at what happens if he compared 6 years in the beginning of 2000 against the 30-year climate record. And the answer was huge shifts everywhere. And that looks sort of like what the climate warming signal looks like in many models. Okay, the US had shifted, and those 6 years were very different from the last 30. Okay, that's because things have been warming. Okay, and the pattern of cooling in the southeast is interesting. It's also seen. So this was not only January minimum temperature, meaning the thaws, the freezes were disappearing in terms of you're approaching less frozen time, you're also having the max temperature going up, but slightly different patterns. This is the most complicated figure, but I love it because this is the prediction of climate normals, effectively. Okay? The black line are the observed changes in the decade of temperature. So it's the 1930s against the 30 previous years, just global mean temperature. It's very simple. And then the 40s drop down. So what happened is in the 1930s, we went up about 1/4 degree compared to the average of the previous 30 years. In 1940, we went up another 1/4 degree almost. That meant successively on top, okay? Then by 1950s and 60s, dropped back to sort of neutral. And then at the end, 70s, 80s, and 90s starts going up again. What's interesting is, the question we had earlier was, these are model predictions. Okay, so the vertical bars are all the model estimates. And what happens is, in the 30s and 40s, none of the models predicted the rise that they saw. The black line's way above the range. They said it should be warm with the greenhouse gas out there, a little warm. But when you start going in the 70s, 80s, and 90s, and I haven't seen the update for this, but I think Francis Weirs will do it, is that it's now predictable. It's a very interesting thing because really it's a predictability issue. Do we know what's forcing the climate? Can we make these predictions? We couldn't do the 40s and 50s, 30s and 40s at all, but we certainly, based on almost all the models, would predict roughly the changes in the 80s and 90s. Now, again, precip regional, no, but in terms of the climate shifts, yes. So this is an era where now we're into a region where we actually should have predictability, okay? Versus an era where we're living with climate variability that was unforced and we didn't really understand, certainly in that one period. So this means sort of different responsibility level, in my view, if you do it. This is, again, an interesting one. If you look at the predictions for the next 20 years versus the end of the century, they depend on scenario. At the end of the century, they don't depend on the different A1, A2, B2, okay. It's an independent scenario for the next 20, 30, maybe 35 years. By the mid-century, there's some spread according to scenario. So it says no matter what we do for the next 30 years, we should be able to make a prediction. And that's what's going to happen in the new fifth assessment report is there are a whole series of climate models being run up to 2050. They're being run at high resolution, they're being run with ensembles, but they're only using a single scenario because it's not worth running different scenarios for these runs. And so they're going to be used for the near-term climate predictions, or estimates of what might happen, which is going to be effectively climate scenario dependent. Before you said, oh, well, it depends on what we emit, what scenario we're following, but that's not for the next 30 years. That's by the end of the century, it makes a big difference. So anyhow, so this one I really shocked me because I finally looked this up recently. And it's really great because if you look at the first and third verse of this song, it's really a hoot, okay? The first one is about sea level rise, okay? You catch that one fairly easily. And the third one is about the government action. And so I found from 1963, it's sort of an interesting climate change song that should be revived somehow. It's really quite amazing that, when you think about it, it'd be appropriate today just for the issue of sea level rise and government action. So that was the end of part A, which was quick, sorry. Now we want to get to part B. We get new pictures, okay. And part B, part B. Where is part B? Come on. Desktop. Size. We know what the sizes are beyond belief, so where's the big ones? Okay, there we go. Part B. Okay. All right. So this is more fun and games about what happens various times. Got it. Okay. So this is a picture from campus. Okay. And on a good day, you can see the Hollywood sign. And you can see downtown LA too. It's quite astounding. I figured that was March too. It wasn't even February. So but it was winter time, so I figured it's what you pulled off in the morning. It only works this only works in the morning. Do you know why this only works in the morning? It's like 7 a.m., 6 a.m. Any idea why it only works in the morning? I mean, those buildings are 50 miles away, right? And the Hollywood sign's about 60 something, right? Why does it only work in the morning? No, okay. What happens during the day? The air heats up. The boundary level rises. It gets filled with aerosols and dirt from all the cars and everything else, small amounts of aerosols. 50 miles through horizontal and boundary layer aerosols, you don't have a chance. This is before the heating of the surface, so everything's quiet down, the air is clear, there are no particles. So what happens after about 8 a.m. is pop, it disappears. And not just smog, but just dust and particles left with it. Okay, we have the convention, we've gone through that one. Let's get through this part. We've done the working groups, this was meant for longer ones, okay. So let's look quickly at the second and third assessment reports. What happens in the evolution? So these are the climate change statements, and interesting. This is the climate change statements of these. And it's interesting, because the first two I've actually sat through the meetings that wrote them. The third one, I didn't get to that one. I didn't do the last one. But the first two says the balance of evidence suggests a discernible human influence on global climate. That was the major headline from Attribution, Did We Cause It? Okay. That thing took a day of fighting. It took a whole half day of half the people meeting a sidebar to fight over it. It got brought up to plenary. It nearly got voted out of plenary by Kuwait and Saudi Arabia. And when they objected and refused to allow it to pass, Bob Watson said, it will be duly noted that everybody agreed on this except Saudi Arabia and Kuwait, whereupon they backed down because they did not want to be listed. It was very interesting. I mean, they actually wouldn't back down until they said, okay, we will put this statement with a note that it's bracketed text, it's unagreed upon text, it's bracketed text, and we'll note that everybody but Saudi Arabia and Kuwait objected to this. Would agree with this, at which point they decided, okay, they would let it go. Very interesting, okay. So that one went through, that was a fight. The next one got fairly easy. There's new and stronger evidence that most of the warming is attributable to human activities. It's getting softer, but yeah, okay, but new and strong, you have to say something's learned something, so that's an update. And then you get to the last one from 3 years ago. And now it says most observed increase in globally average temperatures since the mid-20s, very likely, asterisk. You have to look up very likely. It means something, it's a code word for like 90 percentile. Due to the observed increase in anthropogenic greenhouse gas concentrations. Okay. It's not catchy, it's actually a stronger statement, but it's even more confusing if you're trying to get something to the public. Governments are fine, they know what it means, they realize it's a bit stronger, but as I said, in terms of trying to get something to the public, the first one was a far more powerful public statement, and it caused actually far greater uproar in the Wall Street Journal in 1995, all of it was a big owl over that one. Okay, so where does this get reported? Okay, this is COP 7 in Marrakesh. I really wanted to go to this and I didn't get the invite. They invited about 6 people from Working Group 1 and chapters to present the stuff, and I missed the damn invite. Really annoying, because I really wanted to go to Marrakesh in 2001, didn't get to go there, see the campus or whatever. But we did get to go, a bunch of us got invited to COP 6, which was in the Netherlands the year before. This was the Conference of the Parties, the 6th one after the Framework Convention. Okay, started in '96, so this was in a big meeting room, big screens, bad TVs in 2000, but projection devices, the person speaking up front, huge rooms of people falling asleep. I also got invited to COP 13, which was Bali, which was greatly worth it. Okay, COP 13 was fun. Well, we actually got invited to give a presentation there. So our group, we did some work for the Framework Convention on Brazil proposal on attribution of climate change. Scientific, could you do it? So we actually got to do a presentation, which was great fun. Mind you, that some people showed up, some didn't. It's a 3-ring circus. Okay, what's going on? And it's 2 weeks long. I think I went for 4 days. So what does it take to actually write an IPCC assessment? Okay. This is the calendar for last time. I don't have the calendar for 2013, but this is the calendar 2007. This is what we got given when we were invited in 2004 to become lead authors on the assessment. Okay. So if we look at that thing, what does it look like? There are 4 lead author meetings. The rest are deadlines, drafts, doing whatever. We're looking at a period of 2004 through 2007. It's about 3 years. Okay. There are 4 meetings. We got one in China. That's the red one. Okay, so you at least learn about weather and climate in China. This was the lookout in my hotel room, which was really nice the day we arrived. This was 1 day later. It's an identical look, okay? You could taste the grit when you walked outside. It was basically, it was not pollution, it was the dust, basically. Beijing is really close, and all my friends, my colleagues here warn me, don't go there in May, because that's when the meeting was, because then the storms come off the desert, and it does this. Basically, that's basically desert dust. So it's quite amazing. I was shocked at the difference between the 2 parallel pictures, literally 1 day apart. You get to watch scientists look nerdy on buses. Okay, and then this is the interesting. This is the last meeting. This is the scale of a chapter. This is chapter 1 last time. Okay, this was the group of people who put together chapter 1. And so this was our last meeting to do it. And what we were given is we have this is the third. We've gone through 3 drafts of this chapter. Okay, since we started a zero authority draft in 2004, doing the outline and started drafting sections. This is now 2006. This is the 3rd time. What do we got? We got review comments. Chapter 1 is the least important chapter, okay? It's the historical chapter. We try to say what was important, what's not. We do a sort of history of the IPCC. We do various other things, okay? This is not a high contest chapter, you normally think, right? So, we have expert and government reviews. Governments get sent stuff, the experts get sent stuff, and we get 70 pages of reviews on our chapter. 70 pages, and each page starts like this and then looks like this. So it's all the detailed comments starting on page 1, and we have 70 pages of these things, and it goes through page 7, and then we have please respond. So we're supposed to write our answers in and fix the text, and where we don't do it, we get nasty things back from the support unit, whatever, saying you didn't answer that question, and I didn't feel like it. And it finally goes on down to page 70, okay? So we had basically that time to go through 70 pages of review. That's the 3rd review of the chapter. This is a heavily peer-reviewed document, painfully so. And I said, why 70 pages on chapter 1? I cannot understand it. I mean, the series, some of the chapters had 150. Ours was not the most serious chapter, obviously, but geez, it was painful. Then what happens at the plenary? Okay, the plenary, everything comes together. You write your summary for policymakers, you get your chapters, okay? And so what does it mean for the authors? I love this. So this is 3 years. This is what I've been living with, is this sort of typewriter draft and whatever. We have 3 years of this draft stuff. This thing looks like crummy stuff. This is your chapter. This is what keeps going out time after time again. And all of a sudden, at the end of the plenary, well, actually it takes about a month or 2 thereafter, it gets typeset. You get to look at your chapter and realize how pretty the figures look and how nice it looks when they set it up and put it in the document, sort of the one great threshold. So when you're done with all these line numbers, you can actually just see the final result. It's a great delight, okay? You get to see nice typeset out, you get a little executive summary, okay? This is the final plenary. I didn't go to this one in February, okay? So there's Martin Manning, Susan Solomon, and Chin Da-Hae. And so they're up there at the podium, they're clapping. Why? Because at the end, you can see the screen with the crossouts, whatever. This is something like 1 a.m. of the last day, and they're finally done, okay? And so this is the rule, this finally is the report. The report is prepared in accordance with the rules and procedures, okay? Da-da-da-da. Drafts were prepared by the authors, 30,000 written comments were submitted, 650 individual experts, okay, da-da-da-da. And now the key thing is the summary for policymakers is approved line by line. And did they say this one? No, they don't. But the chapters are accepted. So the difference is the chapters come in and the governments accept the policies. This is like the technical summary. They're accepted, meaning the process was due. You did due process, you followed the rules, and you did it. Whereas the summary for policymakers has gone through literally word by word with the governments and the scientists there. And they're questioning everything. Why do you say this? Can you say this better? What does it mean? Okay, I'll show you some examples. It's a totally different process. Literally, it is word by word, okay? Whereas the chapters, the only verification is the process. The reviews were done officially, they were responded to, and the due process occurred. Same with the technical summary. It's an accepted document. It's not an approved document. So subtle difference between approved and accepted. Actually, big difference, okay. So it's plenary-like. The one in the lower left was Madrid in 1995. That was a long time ago. That was the 1995 report where the first one was. The one in the back, the picture is the people in the background are from the plenary for the synthesis report in 2001. Okay. This was Beijing, the front table in 2001. Not Beijing, this is Shanghai, 2001 summer. So in this one, there were only 99 delegates. It was January 2001. It was very interesting because the US government delegation were still Clinton, and this was exactly the inauguration. The last day with the inauguration of Bush coming as president, okay? So it was a really interesting time, and the US delegation were laying low. They were not being helpful, and Bob Watson in front was yelling at them. They said, listen, if our fingerprints are on this document, then the next administration is going to say, no, we had nothing to do with it. So the US delegation was literally laying low. They were trying to be helpful. Usually they're very helpful. They're trying to get the process moving. But this time they were trying to be very low level. They didn't want to get involved in any fights because they didn't want to be noted visibly as having a Clinton-esque touch on the Summit for Policymakers. It literally was approved the night of the inauguration. Okay, it's done word per word. What interesting things happen? All sorts of odd things happen. So on the 18th of January, Jean-Pascal Van Ypersel, who was a Belgian delegate, he's a scientist, but he was also representing Belgium as their foreign ministry. A lot of governments actually have scientists in this position, but the US, China, whatever, uses total non-scientists in their delegation. They'll have some backup, but they're negotiating people really out of State Department, Foreign Ministry, whatever. They don't let the scientists play things. Belgium, it really doesn't matter because the EU's doing it. So there'll be scientists working with them. He really wanted us to say that there was something wrong with our presentations and we should show something unique. There were figures scattered throughout the chapter. He said, we need a much better figure for the summary that we don't have. And so what we had to do is overnight on the 18th, we had to take figures from three chapters. If you look at the figures, they all have different scales, they all have different timelines, some have different figures. Overnight, we looked at the figures, we managed to clean them, cut them, paste them, and stretch them. I managed to actually know how to stretch them, whatever, and produce, literally overnight, this figure. So we had sulfur, we had various gases, they all lined up, and we all saw them together, and that's exactly what the delegates wanted, and they loved it. And we loved it, actually. It's a much better thing, because the point was it was divided up amongst the chapters, and this was the case where the summary actually produced something better than the individual chapters. Why? Because the government said, this isn't working, you don't have a coherent picture. Okay, this was a positive interaction, it truly worked. Okay, one of the things I also did on this was, given the next I decided to do temperature. And so if you plot the temperature together from different chapters, the temperature is now down below. And the one on the bottom is the 1,000 years of temperature measured by ice cores and other things and boreholes and temperatures. And then the next one was another chapter that did the projections in the future. And so they were all square boxes, so I stretched each of them to be the same scales. And when you put the temperature on top of the future, on top of the temperature in the past, it's quite stunning. If you put them next to each other in the original pictures, they all look the same because they're all plotted on a little square box. They all go like this. But you don't realize that this one scale is 3 times the other scale, and this scale is collapsed by a factor, whatever. So literally, the temperature scale is 2 square boxes that have been rescaled to be the exact similar scale and time, whatever. So I did this one also and gave it out to the delegates. There was a loud gasp. They decided they really were not ready for this yet. The other one they could live with, This one was fine. It's all for the other gases. This one they decided was a little bit edgy, and since the governments hadn't seen it, they did not want to try to get it approved in the next to the last day of the summary. So that's too bad, because it's really sort of a little bit shocking, right? So, but anyhow, the synthesis was 6 months later, so they redrafted and decided they should do it. So it got in 6 months later in the synthesis report, showing that basically what the time scale for temperature change is dramatically different in the next 100 years than it has been in the last 1,000. And that's effectively important, that the rate of change is just hugely different. So it did make it in the synthesis, but they decided that one day the governments were not going to approve it. So this was, in London was an interesting time. This was the synthesis report in 2001. And there are a bunch of scientists. This is very funny. This is odds and pictures I took outside. The scientists are up front looking bored and falling asleep. The US delegation is, State Department people are here. This is the US delegation, including some SF people. This is the Saudi delegation, okay? Various other people are having a horn. This had an interesting battle. The issue was temperature warming, the things, and so the original summary for policymakers had this statement: globally is likely in 1990s the warmest decade, and so on. Insufficient data available prior. The Chinese delegation wanted to scuttle this, so what they said was, well, what about the Christine Spencer stuff about the warming in the troposphere? There's disagreement, everything else. So the underlying report, which is not the summary, has this long paragraph explaining mid-tropospheric warming, how it agrees and it doesn't agree. There are differences in some things. But basically, this is this long section about what's happening in the lowest, in the sort of 8 kilometer in the troposphere, basically. And so this was the underlying report. And so the Chinese delegation wanted to put that in this one, but this was all the space we had to do temperature. And so there's a problem that we couldn't put in anything to explain this complex situation in one line, was the hard part. So they wanted to put almost all of this into this one little short at the end of this paragraph. And the answer is you could do that, but then the whole report starts bloating. And so this was a bloat problem of, yes, you have an underlying piece of fact, how do you summarize it? And it was really very tough. So what happened was they wouldn't agree. They were holding up the entire approval of the section. They just wouldn't let it go. So John Houghton, who was chairing the session in charge of Group 1 and whatever, and the Saudi delegation sort of agreed to meet for lunch, and there was a fight between, we were the authors, so two of us had to go along as the scientists saying, we'll tell you the facts, how do you want to say it? Because it doesn't matter how you say it. It was quite an interesting battle. Houghton actually stormed off in the middle. We had an hour and a half lunch, which all we did was fight with. Houghton gave up and said, if you're unwilling to actually come to any intelligent compromise, there's just no point in doing it. And he literally, stormed off. And he didn't do that. And he may have planned it. He did. The Saudi delegate was so taken aback, he said, well, how can we fix it quickly? We told him how. We put in one sentence at the end. They came back after lunch and said, we agree. It's a very interesting mix of, I don't know how it worked. I think Houghton must have planned it, but I was surprised. He was really angry. I've never seen him blow up at somebody like that, because he's always a fairly smooth and careful person. But when he had to meet with those guys, and after an hour they got nowhere, they kept saying, no, he said, well, if you're unwilling to think seriously about this, just forget it. And they figured this was really bad, so they actually agreed to one little temperature insert. So we got away with this. This became the summary and survived. And then later, of course, became a non-issue. Aviation was equally fun. In 1999, we did a special report, not an assessment report, but a special report on aviation, what it was doing in climate. Okay, I led the climate chapter on it. There were about 7 chapters. We're doing climate change. Basically, the underlying report points out that aviation is responsible for maybe 3.5% of the total impact on climate today, at present. Okay, so that was the underlying report. That is accepted as fact. Now the question is, how does it get into the document? How do you use that in the summary? The governments can say, I want this fact mentioned. So if it's in the underlying chapter, the government say, well, this is highlighted, you said it, you agreed on it, how do we use it? So this was the original draft, and I found my old scribbled notes. It says radiative forcing from aviation, I wrote, is about 3.5% of the total forcing in 19, okay. And some of it wanted, it's as large as 3.5, and others wanted it's only 3.5. And the fight was literally over what was going to go in front of the 3.5. Because the European delegation wanted it's as large as this, it's huge. The Russia and the US wanted it's only 3.5%. And so the choice was literally over the wording. And we end up getting the about in, and this was the final thing where everybody initialed off on it. Everybody to sign, all the delegations to sign off on it. And the Swiss delegation was, as usual, the Swiss delegation was the clever guy. He got everybody to agree saying it's a compromise. Everybody was unhappy, especially that Norway was really unhappy, and I think Norway and Germany are really unhappy. And he said, hey, it's a compromise. Nobody's happy. He said, great, we've got it. So the idea is nobody was happy with the resolution, so nobody won. Therefore, this was a compromise. So that was the final statement, and that's what went into the basic thing. So it's pretty funny. Now, what does the government plenary do to this? What I've given you, you have available, is the document that went in before the plenary, which says restricted. It's the non-typeset document on the left. It's from October. It went into the January plenary for the IPCC one. This is the SPM before it was changed. And so if you look at things, I just did a quick summary of the differences. The figures are the same. Figures are the same. Figures got blue in the background. This figure wasn't in the original one. The governments wanted a timeline in. The figure on the right got put in by the governments. Okay, that figure was the same. A table got put in because people couldn't figure out what was going on in the text. The governments wanted a table instead. So you can see the thing on the right got put in the government plenary. That didn't change. Another table got put in on sea level issues. Okay, and then you go through word by word and start seeing some very interesting and funny things. Some of which are interesting. Let's see. The more interesting one is, let's see, where's the the tropical cyclone ones got again rewritten. The blue, the black is the original and strikeout, and the blue is the new one. This one got carefully rewritten both by the scientists and the governments there because it was confusing in the first place, and they were worried that it was actually going to be wrong. So you can see various things go on during the government plenary. And in general, the governments have an agenda. Some of them have an agenda just to make it cleaner. Some say it can't be translated. You have to write better in English because the core document's in English and that has to be translated in 6 languages. So there's an agreement on what fits or doesn't fit. One time the fight was over few or several, and some pointed out that few didn't translate properly. And French or something. Things didn't quite work. Okay, what about AR5? That's coming online now. This is the 5th assessment report. It's due 2013-2014. There was a scoping meeting in Venice a year ago, more than a year ago, July 2009, okay, in which the IPCC started their view of what was going to happen. That's Chris Field. That's a bunch of nerds in the lower right in these gorgeous meeting rooms. What a waste of the meeting room. These really lovely places that they took us to in Venice. But basically the goal was to set out the chapters for the 5th assessment report. And so you have various documents like straw outlines here for working group 2. Okay, so this is what they proposed, and then we got together. I went there for working group 1 and 2 both, and so I had proposals, I had slides. I wanted a thing on air quality and changing climate, working group 1 and 2, so this was my slides. I was arguing for what should be in the chapters. I wanted something on verification and attribution of greenhouse gas changes. Issues how much the CO2 rises exactly fossil fuel, how much is other things. Okay, these are things I thought were relevant. We should be able to get in there and be evaluated. Does it mean that the science gets done? It depends. It means that it needs to be evaluated. And the IPCC will hopefully say, if we're going to do this, some people may do the work, but then effectively they're limited by what gets published in the literature. Okay. Then we left Venice with a series of 3 outlines that got sent to the plenary. Okay. The plenary, the IPCC plenary is governmental. Plenaries are almost always governmental. Science meetings are closed. Okay. The chapter meetings are closed, they're not public, but government meetings are open to any NGO. Anybody can register as a non-governmental organization and attend the IPCC plenary or a conference of the parties meeting. So after the scientists get through squabbling and worrying and coming up with some agreement amongst themselves, and the new co-chairs take over their sections, then what happens is you actually have a intergovernmental panel change summary of the session. This is governments. This is not scientists. The only people who are truly members of the IPCC are the governments. The scientists are the working people who do it, get appointed, do the job. And so effectively the Nobel Prize actually went to the governments, or should have gone to the governments, because they're the ones who are long-standing. They always have standing memberships as running it. So one thing to note, this is END. How many of you know END? Okay. Very useful. Look it up. Don't forget them. They're in Canada. They do all the reporting. They have people out there who will do all the COPs. They don't do IPCC too often because they couldn't afford it, so they did somebody to summarize it. There'll often be daily bulletins from the meetings going online. Okay. And so this was where it was approved. And it's sort of fun to read these, especially if you've been working on it a bit and then you don't know what happens when the governments get it. You get various funny things. So this was the meeting to do the scoping. So the governments had to approve what the scientists proposed in there, or say, I want something else in there. They wouldn't throw it all out. They would say, literally, I would like to see something else, right? You know, let's change the title of the chapter, things like that. But then you start with all this hilarity. This is the reporting. France, Germany, Venezuela, and Sweden suggested including social structures and systems, and other cross-cutting themes and dedicated chapters, Venezuela called for including indigenous and cultural aspects. Austria stressed uncertainty should be dealt with in a consistent manner. Okay. Was it New Zealand and Brazil wanted greenhouse gas metrics? Japan suggested that Article 2 be considered in the SEER, the synthesis report. So these are icons holding up their flags saying, I understood this. And this is the opening session. So everything is chaos, okay? And then finally you get down to, I love this one, the regional aspects be dealt with, and finally the US says, let's get back to work. Our job here is to approve the working group outlines, not to worry about the synthesis report, which is way in the future. The synthesis will summarize the working groups. So the US is saying, I love it. It's time to get back to work, because the job really is to approve it. So then finally they go through various other things. Working Group 1 presents their thing, so Tom Stocker and Shindahe, who are in charge of Working Group 1, are presenting the outline they got from Venice. They're going through it, and then everybody's complaining, the near-term climate change is the one I want to work, that's the interesting one. Norway asked for inclusion of air pollution. Delegates went through Working Group 1 chapter by chapter and so on in the report. US requests inclusion of trace gases. I like this one. China's proposal to leave black carbon was met with strong opposition from US, UK. So they want to take black carbon out of the bullets, and one of the chapters was specifically, the scientists put in there. It's various, and this is sort of, some of it's being helpful, some of it's jockeying for position. Okay. So you can see what China's after. They don't really want to be, black carbon is another nasty thing, so if you have incomplete combustion in China, you didn't have a lot of black carbon, they don't want that to count or be issued. Thought it was a greenhouse gas. So that's mainly political jockeying, not scientific. Okay. UK wants a bullet on contrails and cosmic rays. Geez, okay. And then there's an argument about prediction versus projection and air pollution versus air quality going on with the government. So this is so it's really humorous. Sometimes it's just, these are like anywhere from 2 to 6 page bulletins you can read through. A lot of boilerplate in front, but then the history of what goes on is pretty funny. Chris Field did Working Group 2, okay. And then the timetable, this is roughly the timetable. So we're looking at basically 2013 to 2014 for the next assessment. And that's the final outline that came out of the approved. So the outline is now approved. The lead authors are now approved, and the bullets are now approved. So now the next lead author meeting for Working Group 1 is taking place in November, and for Working Group 2 in January. So it's sort of finally that's when people gather and start saying, okay, what's going to be in the chapters? There's a pretty close mapping. It's somewhat disappointing. This is the mapping of the 4th assessment report and the 5th assessment report. You sort of follow the chapters. There's some new chapters, but most of them are not that different, which is somewhat depressing. What's worse is Chapter 1 is still there. We had a meeting, we agreed Chapter 1 was a waste of time, let's get rid of it. And somehow it keeps reappearing. Chapter 1, introduction. And you can't say anything new in the introduction because that goes in the chapters where they cover it. It's one of the dead-end chapters. I have no idea why it reappeared again, but it's back. It's like the undead. It's a zombie chapter. It's really frightening. So, anyhow. So there's more slides, there are a bunch of slides I skipped through. They're in the lecture thing. I've given you the documents, which is just the Working Group 1 summary for policymakers and the technical summary for backup. You can download them you can look them up on IPCC or FCCC, but they're posted. Also the FCCC documents with notes on them and highlights, but we'll do that next time. That's posted up on the web now. So, good. So any thoughts or questions about the process, which is more crazy than the actual science? Anyhow, it's sort of it's strange because the governments are both a mixture. I mean, you can really see that the whole thing between them being highly political. Even the U.S. does their own things for their own advantage, but then some of them are really just trying to be helpful because they're just trying to push the process along, and everybody's trying to have people trying to derail it. I mean, for their various purposes, and it's really bizarre. And so you can tell when somebody's pushing their agenda, and all scientists can say that the scientists at these meetings can only correct what's there. So they can suggest wording, but it's not up to them to. They approve the technical part. So if the governments take something out of the chapter verbatim, unless the chapter made a mistake, in which case they're also going to say that's a mistake and we have to fix it, then there's no reason why it can't go in the summary. That's a government call. Okay. So if they're very clever, they start looking at the things they want to find out that they do. From the pieces of the chapter, they have their friends look them up. The NGOs exist. They are allowed to talk sometimes. Depends on the chair. Depends on how busy it is. So the governments will be sitting in the front, and they have their little flags like this, and they put them upright. So it has the name of the country in a block like this. And if you put it like this, then the chair goes through and has to recognize it and writes down and put up whatever. Scientists should not raise their flags. Some of them do. They shouldn't. Because your job is to get this thing done with, get it cleared. It's not to sort of raise issues. And one time there was an author, Chardonnay nameless, who in the middle of the thing started checking, wait a minute, text had been approved. There was a long fight over a paragraph, Once it's hammered shut, it's done. No government can go back and reopen whole thing. So that's why you go word by word. Once you paragraph by paragraph and you're done, it's passed. Okay. So one scientist had the nerve to get up and say, no, he thought he ought to change something in that. We nearly all throttled him because we had other things to deal with to get the rest of it through. And he went back and he said, I don't think that's quite right. And it was just like it was a minor nit that he was picking up. It's not that important. And the text was approved. And he had the nerve to raise his card in plenary. And the chair made a mistake recognizing him. He said, well, I really think we have to go back and revisit that one. And I went, oh no. Because then it reopens up everything. And so it's interesting. IPCC has been called a consensus, but it's not a consensus, okay? It's a bunch of scientists who are supposedly well-balanced, who can review the material and say, what are the most important things, okay? And if there's a big disagreement and there's no scientific resolution, then it should highlight the non-resolution, but it doesn't have to be a consensus because people will never agree. The governments, however, work by consensus, but they work by consensus by wearing you down. So any government can actually stop the acceptance of a plan just by keeping raising their flag and refusing to agree to allow a certain section through, like China was pushing in the Synthesis Report 2001. However, in the long run, they will all be embarrassed to death if the summary is not completed. Okay, so any government could keep it actually from being completed. And we worked on 1 till 2 a.m. when it's thought we're going to be done at 6. In Madrid, it's the first one I was in, and it was like the last day. We all had flights out at 8 in the morning. We're supposed to be done by 6. At 6, it was clear we were having a little trouble. Maybe we could finish in an hour or two. The translators weren't getting paid. They were going home. The delegates had to agree to work only in English without translation, which they agreed to do. Okay, so then there was no translation at that point. And it went until 10 o'clock. We thought, oh good, we'll get out at 10. Can we order pizza at 8 o'clock? I said, oh no, we'll be done. Well, at 2 a.m. we finally crawled out. And even in Madrid, nothing was open in the hotel at 2 a.m., which surprised us. And then it was really a god-awful evening. And that's because the governments finally did agree because it would have been too embarrassing to bring home, State Department, whatever, to say you couldn't come to some agreement on what the summary would be. So they can cause all sorts of trouble, but in the long run, that last night, everything gets done. I think even the 2007 one didn't get done until midnight or 1 a.m. They're getting longer and more complicated. They're also getting more visible. 1995, it was a small group. It wasn't that popular. People didn't know about it. It was still fairly important. But 2007, there were press waiting outside, and all this. It was really ridiculous. It was like a 3-week circus, even for the IPCC, not the COP. And so, much greater pressure and everything, both to agree or not agree, or to basically make sure you stick out for your point. So, it just took forever. They didn't expect it to finish till after midnight. And they knew it wasn't going to finish till after midnight, because they had a press conference in the morning. If they didn't come at the press conference, the government's saying, we have solved it, here's our summary, it would be way too embarrassing. And they would be held, it's not the science, they would be held responsible basically for doing it. So they buy onto the document. The summary is their document, it's not their science, it's their document. They agree on the words, they sign off on it. And it's changed the view of the summary that it is now a quasi-governmental document because they've actually helped rewrite it, question what it means, say some things are more important, bring them up. Yeah.
How did the international panel originate? Was it just independent governments working together, or is it under the direction of the United Nations?
Yeah, there's a little blurb at the very beginning, but it doesn't help you much. You can do a better job at looking up IPCC history on the web. But it was formed in 1988, which is interesting, okay, by WMO and UNEP, so World Meteorological Organization, which is the one that collects most of the climate data, physical climate data, and UNEP, United Nations Environment Program, okay? They were the ones, for example, who ran the Montreal Protocol and the ozone assessments, the science part. And they actually, the WMO and UNEP people were the ones who actually organized the Conference of the Parties for Montreal Protocol and whatever. So it's the secretary of UNEP, Tobel was what started the initial Montreal Protocol type stuff. So they knew that climate was an issue. In 1988, they formed the IPCC because Bert Bolin and John Houghton and some of the original IPCC leaders knew this was coming online. They knew the ozone work. They knew they had to have a way to set up to do climate assessments that was not done nation by nation. Okay. So it's interesting because that meant that they knew that in 1990, in Rio, there was going to be a push for a Framework Convention on Climate. The Framework Convention on Climate was not signed off until 92 by the governments. It wasn't ratified until 94. The Framework Convention was basically initiated in 1990, but people knew, and the governments knew this was going to happen. was sort of the Rio Convention in 1990, okay? Therefore, in 1988, they sort of got together, got the IPCC going actually ahead of the Framework Convention. But in anticipation that there would be a Framework Convention and that it would need scientific backup. So IPCC does not speak directly to the COP, basically, even the scientists. There's a group called Subsidiary Body on Scientific and Technical Advice, SBSTA. The SBSTA is the main body for bringing science into the COP. So when we went there to test, we went there to give a report on some science projects we've been doing, and we reported to SBSTA. SBSTA has their meeting at the Conference of the Parties. They're the subsidiary body. It's the same delegates, they group them, but it's for bringing in science. So SBSTA sort of approves and clears the IPCC and passes it on to the Conference of the Parties saying, here's what we're going to negotiate on. So it's an intermediary body that you work through. So the IPCC is, the conference, the climate convention is just very complex. All sorts of structures and rules and crazy stuff, okay. And then the IPCC has its own problems, but that feeds into sort of the science side. There's a subsidiary body on implementation, which has to do with clean development and how you would implement this and everything else. So there's a body on implementation, a body on science and technology that sort of gather together the information, the documents, and whatever that then they will push forward to say, okay, here's. So IPCC was anticipated. They clearly knew it was coming. It's interesting. I mean, they knew a framework convention on climate was something like it was going to be online. So they actually did it ahead of time, which is unusual. So it predates the framework convention. But it was set up by the UN. So it was set up as, you know, I'm not a member of the IPCC. I do IPCC assessments, okay. Members of the IPCC are, I think, people like Co Barrett, somebody from EPA, and somebody, Trig Kelly from state, are the US reps for the IPCC. They go to the government meetings for the IPCC. They talk about the budget. They say when the assessments are going to be due. So the governments get together and say, okay, when's our next assessment going to be doing? They actually plan and they say when we want it. They sort of ask for it at a given time frame. They're planning, part of the time frame is to make sure that all the stuff gets delivered before a major conference of the parties. So they'll plan it so that the synthesis report will be delivered in, say, October. And always the conference of the parties meetings for the climate convention will always be end of November, December. So there'll be a cycle where you don't want an IPCC major result delivered in January. At least, you know, because then you're sort of hinting at what it is. You want it hard and delivered in September, October, November, so that at least if there's a meeting, everybody can agree, here's the document. So there's a lot of timing issues. Good. Sorry to run late. I'll be shorter next time.